This is e-mentoring session for ch102. I am Nikhil Sharma and I will be your e-mentor for the rest of the semester. Today we are going to discuss topic 9, substitution and elimination reactions. Alright, so I'm going to use the course notes provided on the Moodle shell so that it's easier for you to follow. Alright, there are two types of substitution reactions, nucleophilic substitution reactions, SN1 and SN2. SN1 deals with a stepwise reaction. In other words, it's a unimolecular reaction, and SN2 is a bimolecular reaction which usually takes place in just one step. Alright. The rules for the reaction depend on the type of alkyl halide, the type of nucleophile, the nature of the leaving group, and the nature of the solvent. We'll discuss this further as we go along into each of the reactions. So first we're going to go through SN2 reaction because this is a lot easier, and since it's a bimolecular reaction, it only takes place in one single step. So as illustrated below, SN2 reactions take place in one step. In other words, the nucleophile gets attached to the electrophile at the same time as the leaving group leaves the electrophile. So these are dependent on a few things, the alkyl halide. So, excuse me for that. Right, so the less the steric hindrance of the alkyl halide, the faster the reaction will be. In other words, the less branched this alkyl halide is, the easier it will be to form for the reaction to proceed easily. Therefore, SN2 reaction favors primary and secondary reactions only. SN2 never undergoes a tertiary alkyl halide. Tertiary alkyl halides are those halides which will not have any hydrogens attached to the alpha carbon. Therefore, its steric hindrance will be a lot higher and it will not undergo SN2 reaction at all. Hopefully you can hear me properly and you're following it easier. If you have any questions, do send me a chat and I'll answer it for you. Okay, the second nature which determines whether SN2 reaction will proceed is the type of nucleophile. SN2 reactions usually
you are currently the only person in this conference.
Are associated with SN2 strong nucleophiles. So a strong nucleophile is required in general for SN2 reactions. Third is the leaving group. The three main leaving groups we are going to deal with are iodides, bromides, and chlorides. Iodide is the lower you go in the halogen group, if you go down group 7 in the periodic table, the lower the halogen is, the easier it is for it to leave the electrophile, the alkyl halide to form the electrophile. Therefore, iodides will always leave much more easy than bromides, which will leave much more easy compared to chlorides. And the last one, which determines the nature of SN2 reactions, is the type of solvent. So these are polar aprotic solvents. Aprotic meaning they do not have a hydrogen or a H+ ion attached to it. So it's basically in a basic medium, a OH- is usually what it is used. So for the questions, I'll go over a few of them since we have time. So The question is which alkyl halide in each pair will undergo SN2 reaction. So you are looking for primary and tertiary alkyl halides. Are you able to hear me now? Stella? Are you? Hello? Okay, I'm gonna continue since this session is being recorded. If you are not able to hear me, do let me know. So for question 1, SN2 reactions, since they favor primary and secondary alkyl halides, we are only gonna consider which one of the pair will much more easily be able to undergo SN2 reaction. So this is a primary alkyl halide and that's a secondary alkyl halide, since secondary alkyl halides are only attached to one hydrogen. Alkyl halides are the halogen in the molecule is always attached to a alpha carbon which is connected to two hydrogens, whereas a secondary is alkyl halide, the halogen is attached to the alpha carbon with only one hydrogen. So of these two, both will undergo SN2 reaction, but primary alkyl halides will undergo SN2 reactions much more easily as compared to secondary. So SN2 will favor that one, but both of them will undergo primary SN2 reaction. As part B, this is chloropropane and bromopropane. Here, since the only difference between the two is the leaving group, so you have to determine which leaving group is better compared to the other one. So we're going to go back to part 3. So as the sequence shows that iodides are better at leaving than bromides, which is better at leaving than chlorides. So here we're comparing that sequence to this question. Chlorides, since at the end, they will find it more difficult to leave the molecule as compared to bromides, since they are better compared to. And if there was an iodide in either of the molecules, then that would be undergo SN2 reaction much more easily. So both will undergo SN2, but of the two, bromopropane, will undergo SN2 reaction much more easily. Okay, part C, you have a secondary alkyl halide and a tertiary alkyl halide. Tertiary alkyl halide are alkyl halides where the bromine or the halogen in general is bonded to a alpha carbon which is not bonded to any hydrogen atoms at all. So that's a tertiary alkyl halide. So of the two, we already know from alkyl halides that secondary alkyl halides never undergo SN2 reaction. Are you able to hear me? Alright, so I'm going to continue. We are discussing the nodes which are on Moodle, and we have just started discussing self-test 9.1. So we are up to part C. At the moment we are discussing whether this molecule or the tertiary alkyl halide will undergo SN2. So with reference to part 1 of the factors which determine the reaction that follows SN2 mechanism, it's clearly stated that tertiary alkyl halides never undergo SN2 reactions. So regardless of the fact that both the leaving groups are the same, tertiary alkyl halides will never undergo any SN2 reactions ever. So of the two, the secondary alkyl halide is much more easily able to undergo SN2 reactions. Part B is okay. Steric hindrance. Steric hindrance is basically the repulsion between two substituents. Like here, the methyl is a substituent, and that methyl is a substituent as well. Hopefully, I can go. Okay, this is not working. How do I explain this? Two components of the two substituents, right? So hydrogen has, methyl has 3 hydrogen groups attached to it, and this methyl also has 3 hydrogen groups attached to it. So what you will see is this hydrogen from that methyl group and this hydrogen from that methyl group is extremely close to each other, and since they are both hydrogens with the same charges, they will repel each other. So that's basically what steric hindrance is. It's when the components of the substituents are able to repel each other. And the more branched it is, or the higher charged it is, or the greater electronegative atoms that is attached, the greater the steric hindrance is going to be. Hopefully that answers your question. Alright, moving on to question number 2, since I can't actually write on this easily. What I'm going to do is just give you the mechanism briefly. So this is a primary alkyl halide, and once the bromine here leaves as a leaving group, and this nucleophile will attach to the carbon. So those electrons will leave, giving the carbon a positive charge, which will attract the nucleophile. So it basically is a substitution reaction So what happens is bromine will leave and the hydroxide ion will attach to the carbon at the same time. So since it's a one-step process, both of these components happen at the same time. For part 2, similar thing is going to happen. Since fluoride is more electronegative than the carbon, it will pull the bonding electrons toward itself, leaving carbon slightly positive, and which would attract the amide to the carbon. Yes, so we are basically going each section by section. So currently I'm discussing SN2 reaction. Next would be SN1 and then E2 and E1, and that way we'll be able to cover all 4 of those and you'll be able to determine the difference between them. So the last one, similar thing, you can do the same thing as the first 2. Yes, so basically what I will be doing is I'll first give you a general one, discuss the general one, and then as a self-test one, I'm going to discuss those as examples so that you can follow it much more easily. We are still trying to figure out a mechanism in order to draw it on e-mentoring. We still have not figured that out yet. Hopefully we do it by next week. But currently, I'll have to resort to writing. Sorry about that. Okay, since we have already discussed everything, that's everything on SN2 reaction. All you have to figure out in the first step is the type of alkyl halide, which whether it's primary, secondary, or tertiary. Tertiary never undergoes SN2 reaction. It always has to have a strong nucleophile. The leaving group, the nature of the leaving group, the better the leaving group is, it's more easily able to undergo SN2 reactions. And the nature of the solvent, it's always polar aphotic solvents. Next is SN1 reaction. SN1 reaction is a stepwise reaction, so it basically undergoes 3 steps. One where the leaving groups leaves the alkyl halide. Next step is when the nucleophile gets attached to the alkyl halide, or the alkyl group, which would be a carbocation now. The last step is always deprotonation, which would stabilize the product. So as usual, we are going to go into factors which determine it first. So alkyl halides, it's totally opposite to SN2 reaction. SN2 reactions favor primary and secondary alkyl halides, whereas SN1 will favor tertiary and secondary alkyl halides. Primary alkyl halides and methyl groups never undergo SN1 reaction. Also, once we are going to see this part in the examples, but once the halogen leaves the alkyl halide, at times the molecule is going to arrange itself, so the carbocation is going to arrange itself to a more stable form. We're going to see this once we look at the examples. So the next factor determining this is the nucleophile. As opposed to SN2, which uses strong nucleophiles, this reaction uses weak nucleophiles. The leaving group is same as SN2. Iodides are better at leaving than bromides, which is better at leaving than chlorides. And lastly, the fourth nature of factor which will determine SN1 reaction is the nature of the solvent. These use polar protic solvents, and SN2 reactions will always use polar aprotic solvents. Okay, looking at this example, in step 1, the leaving group will leave the alkyl halide. Since this is a secondary alkyl halide which is attached to, where the alpha carbon is attached to only one hydrogen, the leaving group will leave, leaving a positive charge on the carbon. Since the bonding electrons is attracted to the bromide will take the bonding electrons and leave, leaving behind a positive charge on the carbon. Now, since now it's a secondary carbocation because it's attached to just one hydrogen. This carbon is only attached to one hydrogen and two alkyl groups, this one and that one. It can be seen that if this hydrogen moves from this carbon to that carbon, then we can actually form a tertiary carbocation. This stability thing will always happen. You will always have to look at it when you are doing SN1 reactions. Otherwise, you will get a totally different product right at the end. So, this hydrogen will move from this carbon to that carbon, leaving behind this carbon with a positive charge. And since this carbon is not attached to any hydrogen directly, it's only attached to 1, 2, and 3 alkyl halides, like 1, 2, and 3 alkyl halides. This becomes a tertiary carbocation. In the next step, the tertiary carbocation is going to attach to a weak nucleophile. This is methanol, and methanol has an OH group, and the oxygen on methanol has 2 lone pairs of electrons. These are the lone pairs which will form a bond with the carbocation. So, the electrons will get attracted to the carbocation, whereby the entire molecule gets attached to that carbocation. So once the molecule is attached to the alkyl group or the carbocation, the oxygen is going to attain a positive charge because now it's bonded to 3 different groups: the larger carbocation, the hydrogen, and the methyl group. And oxygens in their stable form only form 2 bonds. So here, since it has formed 3 bonds, it has attained a positive charge. And since oxygen is quite electronegative, it will try to, it's more stable, having a negative charge instead of a positive charge. So what happens in the next step is that deprotonation takes place. Protonation means addition of hydrogen. Deprotonation is removal of a hydrogen. So a proton is just a hydrogen ion, a H+. So deprotonation is a removal of the H+ ion. So what happens is, in order to gain stability, this hydrogen is going to leave behind the bonding molecule, the bonding atom, electrons to the oxygen atom, and the hydrogen is going to leave. So that hydrogen leaves, leaving behind oxygen with only 2 bonds in its normal stable form, and the entire molecule becomes more stable. Are you with me till that? Alright, so I'm gonna discuss the self-test. Oh, as similar to the first self-test we did. So here is which alkyl halide in each pair will undergo SN1 reaction. So we're gonna go back to the notes. SN1 reactions favors tertiary and primary alkyl halides. Tertiary and secondary alkyl halides. Primary and methyl groups do not undergo, methyl halides never undergo SN1 reaction. So first you have to determine whether the molecule is a primary, secondary or tertiary alkyl halide. So since the halogen is attached to a carbon which is attached to two hydrogens, it's a primary alkyl halide. Here the halogen is attached to this carbon which is only attached to one hydrogen. It's a secondary alkyl halide. So of the two, the secondary alkyl halide is going to undergo SN1 reaction only, since primary alkyl halides do not undergo SN1 reaction. For part B, we have a secondary alkyl halide and a tertiary alkyl halide, since bromine is attached to a carbon which is not attached to any hydrogen, only methyl groups. So this is a tertiary alkyl halide. Tertiary alkyl halides always undergo SN1 reaction. It's very easily favored as compared to secondary alkyl halides. Both of them will undergo SN1 reaction, but tertiary alkyl halides will undergo it much more easily as compared to the secondary alkyl halide. Okay, so I'm gonna try to show you the mechanism as best I can. So in the first part, the leaving group is going to leaving behind a positive charge on the carbon. Right, so that's step 2. Step 1, the leaving group goes. Step 2, the lone pair on the nitrogen is going to attach to the carbon, is going to attach to the carbon. So leaving behind the carbon with NH and H with the three methyl groups, right? That's methyl groups. Since ammonia in its natural stable form only forms 3 bonds and here it has formed 4 bonds, it will now have a plus charge on it. And since nitrogen is more electronegative and all electronegative atoms would prefer to have a negative charge on them instead of a positive charge, what happens in the third step is that these bonding atoms will get donated to the nitrogen and the hydrogen is going to leave. So that's deprotonation, which is step 3. Leaving behind a molecule which would be the methyl groups and then the 2 hydrogen groups. Okay, so since the nucleophile obtains a positive charge and in its natural form, in its stable form, it prefers a negative charge on it, the hydrogen will leave the molecule, leaving behind the bonding electrons to the nucleophile, which is now attached to the electrophile. And it's always the lone pair of electrons on the nucleophile which gets attached to the carbocation. So okay, so in part 2, similar as part 1, since it's a secondary carbocation, it will undergo SN1 reaction. The leaving group is going to leave first, leaving behind a positive charge on the carbon. Then the lone pair on the oxygen is going to attach to the carbon, which will give us methyl, that's H, and then oxygen with 2 hydrogens. And since this oxygen now has 3 bonds to it, as opposed to its natural stable form which only forms 2 bonds, this oxygen will have a positive charge on it. And so since this is more electronegative, and it would prefer to have either a stable form of 0 charge or a negative charge, one of the hydrogens, any one of them, can donate its bonding electrons to oxygen so that the charge gets removed and the hydrogen will leave. If you take this hydrogen, then this bonding electron goes back to the oxygen and this hydrogen is going to leave. So that's all you need to know about SN1 and SN2 reactions. So just a recap. SN1 reactions, SN2 reactions, alkyl halides, only primary and secondary will undergo alkyl SN2 reactions. Strong nucleophile is required for SN2, and the leaving group is the same for SN1 and SN2. Iodide will leave much more easily than bromides, which will leave much more easily compared to chlorides. And the nature of the solvent used is always polar aprotic solvents. Whereas for SN1 reaction, this reaction takes place in at least 3 steps. So the first one, the leaving group leaves, forming a carbocation. Then the nucleophile gets attached to the carbocation. Step is always deprotonation to bring stability to the molecule. So the type of alkyl halides that are used for SN1 are tertiary and secondary alkyl halides, and primary alkyl halides, or any halides which are attached to a methyl group do not undergo SN1. Nucleophiles, weak nucleophiles are required for SN1. Leaving group is same as SN2 reaction. The only other difference between the two is the type of solvent that is used for the reaction, and here SN1 requires polar caustic solvents. Alright, moving on to the stereochemistry. So if you have a optically active molecule, in other words, if the central carbon atom has four totally different substituents added onto it, then it becomes a chiral molecule, and the carbon is known as the chiral center of it. Right? So in stereochemistry, you must have learned how to go about labeling it as R or S stereoisomers. So I'm just briefly going to go over it. The more electronegative one atom is, or the larger it is, not the smaller, the larger it is, it gets associated as number 1. Then the next one is it's that carbon attached to the next carbon molecule. So it's always the ethyl group will get number 2. Since methyl is more electronegative than hydrogen, that gets given 3, and then the hydrogen. So what happens during SN2 reaction is that for chiral molecules, when the nucleophile gets attached to the carbon and the leaving group leaves, the stereochemistry becomes opposite. So it changes from R to S. So basically, now when you number these substituents according to their electronegativity, what you'll be given is that, oh hey, oxygen is more electronegative than any one of these other substituents, so this gets 1. Next is carbon, which is attached to another carbon, so is more electronegative than these two, that gets given 2. Methyl group is more electronegative than the hydrogen group, this gets 3, and the last one is 4. So if you draw an arrow from 1 to 3, you'll see it goes from the right to the left. So that is R. And if it goes from 1, 2, and 3 from the left to right, counterclockwise, then it is always given the S arrangement. So SN2, if a chiral center is associated with the alkyl molecule, then there is always an inversion of the stereochemistry. So if you start with an S molecule, you will get an R molecule. So in this case, you started with an R molecule, you will get an S molecule at the end. So similarly, here bromine is more electronegative than the other, so it gets given 1. Then the ethyl group is 2, then the methyl group is 3, and then the hydrogen is 4. So if you draw an arrow from 1, 2, and 3, you'll see that it goes clockwise. So this becomes an R stereoisomer. So once that's an R isomer. So once the leaving group leaves, the nucleophile gets attached to the carbon. What you'll get is, if I can go this, you get hydrogen on top, you get ch2, ch3, oops, ch2, ch3, here you'll get NH2 and then NH3, CH3, sorry. Okay, so now if you label it, hydrogen is much more electronegative than the carbons and the hydrogen, so that gets given 1. Then comes the ethyl group, 2, an ethyl group which is 3, and then the hydrogen which is 4. So if you draw an arrow from 1 to 3, you'll see that it goes counterclockwise. So again, it's an inversion. It goes from R to S. Yes, SN2 will always have one product. Okay, now looking at the optical activity of the alkyl halide as part of SN1 reaction. Here in SN1 you'll actually get two separate products. One will be the same arrangement as your initial reactant, the other is an inversion. So since we only have 9 more minutes to go for this session, I'm just gonna quickly go over this. So it basically follows SN1 reaction. The leaving group will gonna go, leaving behind a positive charge on the carbocation. Oops. A positive charge on the carbocation, then the nucleophile will attach. So the next thing after the leaving group goes, you have to determine whether the carbocation is in its most stable form. So since there is already a secondary carbocation, since it's only attached to one hydrogen, and regardless if another hydrogen moves or does not move, it will still be a secondary carbocation. So once the nucleophile gets attached to this carbocation, we are left with two molecules, that one, and since oxygen is actually an electronegative atom and it has acquired a positive charge now, it will undergo deprotonation. Both of the molecules will undergo deprotonation to form the stable compound. Right, so now so the only difference here is that in this one, the oxygen the water gets attached to the carbocation directly from the top, and in this one, the oxygen from water gets attached underneath it. So it's a back attack, where this is a direct attack. In the back attack, the hydrogen will move to the top, and whereas in this one, the hydrogen remains where it was, as it originally was. In this one, it moves to the top.
You are currently the only person in this conference.